Hello. Oh, wow. Okay. Hello, everyone. Happy New Year. Today we are going to talk about thermodynamics. This is the second to last webinar. We have just one more on the delta function. I'll try to keep it reasonably simple today, with probably one quite sophisticated problem on the means-free path. Whereas everything else is more or less straightforward. I have done a few more webinars on this topic, so you can look back to find some harder problems. Let's put it this way. So yes, so we had some from 2023, some from 2024, etc. Otherwise, let's jump in. So thermodynamics. Thermodynamics is slightly more than you are normally taught in A level. In A level, you do the kinetic theory of gases, but you don't normally touch thermodynamics. You don't study the thermal processes. Thermodynamics is usually limited to cm delta T. Right, so cm delta T, that's the typical cm delta T, that's typical, and they call it thermodynamics, although you don't normally study the first law of thermodynamics and the second law of thermodynamics. We won't touch the second law of thermodynamics today, but we will talk about the first law of thermodynamics, which is usually not covered in the A-level syllabus. But before that, let's just do a question very similar to one in the assignment. The first nuclear test, that is the Trinity test, that was in 1945, contained 10 kilogram of fissile uranium. So assuming that the fission of each nucleus produced one atom of radioactive gas, estimate how much of these molecules you breathe in with every breath. So we'll have to make some assumptions here, of course. So what are we talking about? Well, we're talking about 10 kilograms of uranium. If you watch the Oppenheimer movie, that was the first ever nuclear test. It's 10 kilograms of uranium, uranium-235, and basically it exploded. And let's say it contained n atoms, and now we have n atoms of krypton, maybe? We don't know. I mean, it doesn't really matter. Let's say an atom of radioactive gas. Now this gas spreads, assuming that the first assumption is that this gas spreads evenly across the atmosphere. That's the first assumption. And well, I think that's the only assumption we really need to do. Okay. Oh, the second assumption, we need to estimate how much we breathe in. Let's say we breathe in, I don't know, 3 liters. Assumptions. The gas spread evenly, and one breath is 3 liters. Why not? Okay, so using these assumptions, let's start calculating. First of all, we need to figure out how many atoms. So n is the atoms. So n is the mass of uranium. So that's mass of uranium divided by the mass of a single atom of uranium. And the mass is, well, 10 kilograms. That's the mass of the metal divided by the mass of a single atom. So it's uranium-235. So it's 235 multiplied by 1.66 times 10 to the minus 27. That's the mass. So that gives us the number of atoms, roughly. So 10 divided by 235, 235 times 1.66 times, I think it's minus 27. That's 2.6 times 10 to the 25 atoms. Now we need to find the volume of the atmosphere, right? So we are interested in the number of atoms per breath. So this is the number of atoms in the atmosphere. We need to find the volume of the atmosphere. Volume of atmosphere. Well, atmosphere is a very thin layer of air around the Earth. And the radius of the Earth is 6,400 kilometers, give or take. Now we can assume that the atmosphere is spread evenly around the Earth, and the volume of the atmosphere is 4 pi r squared. That's the surface area of the Earth multiplied by h. H is the height of the atmosphere. Now, an overestimate for h would be 100 kilometers. The problem is the atmosphere is not uniform, so you would have a very dense atmosphere close to the Earth, but as you go up, it gets less and less dense. But let's assume h is 100 kilometers. 100 kilometers. That's yeah. So we can find the volume of the atmosphere. So that's 4 pi times 6,400,000 meters squared times 100,000. So 4 pi times 640,000 squared times 100,000. That's 5.14. Well, 5.1 times 10 to the 19 cubic meters. All right, and that we can convert that into liters right away because we know that 1 cubic meter is 1,000 liters. So it's 5.1 times 10 to the 22 liters. So the number of radioactive atoms, the density, the concentration of atoms is N, is the number of atoms divided by the volume. So that is 2.6 times 10 to the 25 atoms divided by 5.1. 5.1 times 10 to the 22 liters. So we get 2.6 times 20 to the power, well, 2.6 divided by 5.1. So 50, 0.5 times 500 atoms per liter. So 1 breath is approximately 3 liters, which is approximately 1,500 radioactive atoms. And this is only from the first ever nuclear test, which was one of the smallest nuclear tests ever to be done. Total number of nuclear tests, and there were approximately 2,000 nuclear tests overall. So you can imagine how much stuff is flying around from nuclear tests. And actually, nuclear tests can be used to date certain organisms. So, for example, one of the products of the nuclear tests, I don't remember the name of the element, but it has a very similar properties as calcium. I think if I look it up, periodic table, calcium, strontium. Strontium is one of the products of nuclear tests, and it gets expelled into the atmosphere, and it's in the bones of every single one of us. Okay, because it's so similar to calcium, it takes place in our bones, and it plays the role of calcium, but it is radioactive. By examining a dead body, for example, you can test whether there is strontium in the bones or not. And if there is strontium in the bones, that means that the person or animal lived after the start of nuclear tests. Whereas if there's no strontium in the bones, that means that the person lived before nuclear tests. So you could figure out whether a person died in the beginning or the end of the 20th century by just looking for radioactive materials. So every one of us has those radioactive atoms inside of us, and that's a given. And I understand that the Kodak company once sued the American government for damaging their photographic film because they did a nuclear test. They didn't tell anyone, but that damaged the film. You can read about it. The film produced by Kodak. So that was an interesting thing. Okay. Anyways, with every breath, temperature of a room was 10 degrees. So this is an equation of state question, reasonably simple one. So we have a room, and it's 10 degrees. 10 degrees. And the heating is switched on, so it goes up to 20 degrees. And because the air expands, of course, it doesn't increase the pressure in the room because the room is not sealed, so some of the air escapes through the cracks. So as the temperature increases, some of the air escapes. And we need to work out how much of that air escapes. And it's a very, very straightforward question. We just need to write the equation of state. So PV equals nRT. However, we're not really interested in the number of moles. We can write the number of moles as the mass divided by molar mass. Mass of gas divided by molar mass of gas, molar mass. Okay, so we can write PV equals m over mu RT. You could alternatively, you could write N is the number of atoms or number of molecules divided by Avogadro constant. That's another way of writing the number of moles. I'm going to go with this one. It's my preferred way of writing the equation of state, and I just substitute. I find M1, that's before before heating up the room. So M1 is mu PV divided by RT. Now the volume hasn't changed, the pressure hasn't changed, only T has changed. And M2 is of course mu PV over RT2. So I'm interested in the change of mass. I'm interested how much mass escaped. So delta M is M1 minus M2. I'm doing M1 minus M2 because I know that M1 is greater. I'm answering the question, how much is escaped? So I'm not doing final minus initial, as you normally would. I'm doing initial minus final. And that's mu PV over RT1 minus mu PV over RT2. So mu PV over R, 1 over T1 minus 1 over T2. And now I can start substituting the values. So mu is 29 grams per mole, 29 grams per mole, multiplied by the pressure, 97,000 pascals, multiplied by volume. Volume is 50 cubic meters, and then R, that's 8.31. I can never remember the units for R. Is it joule? Okay, gas constant. Joule per mole per Kelvin. Joule per mole per Kelvin. Okay. And then here I have 1 over T1. T1 is 10 degrees, so it's 283 Kelvin minus 1 over 293 Kelvin. So Kelvin cancels, mole cancel, joule. Joule is pressure times volume, so joule cancels with Pascal. So joule can be written as Pascal times meter cubed. All right, so I'm left with grams. That's very good. And I just need to calculate. Well, 29 times 97,000 times 50 divided by 8.31 times 1 over 283 minus 1 over 293, 2,040 grams. Quite significant if you think about it. 2 kilograms. So we lose about 2 kilograms of air in a typical room. Answer 2 kilograms approximately. Okay, that's I don't know if you expected that answer or not. Did you expect more or less, or about that? Yeah. Well, it's not that light if you think about it. A cubic meter of air is 1 kilogram. So a 50 cubic meter room would have about 50 kilograms of air. So yeah. Okay. Now this is the sophisticated question. Estimate the mean free path of helium molecules in a helium balloon. It doesn't have to be a helium balloon. Just helium gas. We do need the size of a molecule, so let's assume that the diameter. Let's take it as 1 nanometer. Okay, so how do we do mean free path? The mean free path is how far a molecule travels before colliding with another molecule. So let's say we have a molecule and it travels. So there are some other molecules here, 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 here. So we can see that the first molecule it will collide is this one, and it will travel approximately this distance. We call it lambda. Lambda is the mean free path. It's the distance traveled by a molecule before colliding with another molecule. How do we even approach this problem? Well, we say, well, what is the condition for it to collide? The condition for it to collide, so if the center of the molecule in question is less than 2 radiuses, radii, away from the center. If the center of another molecule is less than 2 radii, then they will collide. So for example, this molecule, they won't collide because this is R and R, so it will just swipe past. But if if X, let's call this the distance between centers of two molecules is less than 2R, then they have collision. So in order for a particle not to collide with anyone, it needs to travel, it kind of needs to swipe an area of a circle with double the radius. Right? And no center of another molecule has to be in this imaginary cylinder of air. Okay. Does that make sense? Is any clarification needed? The center of any other molecule, so the molecule can overlap with this cylinder, but the center cannot be inside. Because we assume that it is traveling in a given direction. We assume that we know the velocity of the particle. So it's traveling in this direction, and it won't hit anything which is outside this cylinder. Oh, sorry, inside. Yes, outside this cylinder. We also assume that the other particles are stationary, by the way. This is an interesting thing, but anyways. So in order for the molecule not to hit any other molecule, it has to be the only molecule in that imaginary cylinder. The molecule has to be the only one in the cylinder. Okay, so that means we just need to find the the volume of that cylinder. The volume of the cylinder is pi 2r squared. So it's because it's 2r, r and r, 2r, multiplied by lambda. Lambda is the distance by the mean free path. Now, for the gas, we for the net gas, so the volume density of the number of molecules per unit volume, n. Oh, that's bad because we already have n as in number of moles. That's unfortunate. That's I used n here. So volume density. I don't want to introduce any new variable, so I'm just going to go with n over V for the gas. Number of molecules per volume. Archie, I'll come back to this question. For now, we just assume that they're stationary. We will make an adjustment for the moving particles. So N over V, and we know that PV equals NKT. So we can express N over V can be written as P over KT, pressure over KT. So N over V, that is P over KT. And we know that the volume is that. So N divided by pi 2r squared lambda equals P over KT. So we need lambda is NKT divided by P pi 4r squared. Yeah, 4r squared. N is the number of particles in a unit volume. N is the number of atoms. Number of atoms. And V is the volume of a gas. So N over V is the number of atoms per unit volume, per cubic meter. I think what I did, I just confused it with charge carrier density. Like charge carrier density, I think it's N. Oh yes, N is the number of charge carriers divided by unit volume. But yeah, number of atoms divided by volume of a gas is P over KT. That comes from here. And I replace the volume with the volume of the cylinder. Yeah. But we also know that it has to be the only molecule. So N is 1. N has to be 1 because it is the only one. Therefore, lambda is KT divided by pi 4r squared. But that's assuming, well, we did that because we said the molecule has to be the only one in the cylinder. That means N is 1. Okay. Now, assuming other particles are stationary. Particles are stationary. Now, this equation had a very unusual application in the Second World War, in the partisan movement. So partisans, they hid in the forest, and they came out once in a while to do stuff. Let's not get into it, but like partisan warfare. The question was, if you get found out, how far in the forest do you have to run in order that you can't get shot? So what they knew is roughly the number of trees per square kilometer. So how far do you need to be from a machine gun, for example, in order that it is impossible for the machine gun to hit you, on average, of course. And you could use this equation as the mean free path of a bullet through a forest of trees. So quite an interesting application. Yeah, so just it's the same principle, right? You have a bullet. How far can it travel before hitting a tree? And this is how far do you need to run away from well, if you get found out, how far do you need to run away in order for it to be impossible for the enemy to get you? Right, so that's assuming other particles are stationary. Now, what happens if they're not? Well, now we need to assume that you are sitting on top of a particle and the other particles are moving. So you need the relative velocity of you. You need the velocity of you relative to the other particles. But once again, they are all moving randomly, so you need to take an average. So let's assume that the particle, you are particle A, and that's the velocity of particle A. And another particle has a velocity VB. So the relative velocity of A, or velocity A relative is velocity of A velocity of A relative to, sorry, velocity of A relative to B is V, is it VB minus VA? Sorry, I think I confused myself. So if you have, this is your moving reference frame, so VA. Of course, yes, it's VB minus VA. VA minus VB. Sorry. VB minus V, sorry, VA minus VB, of course. Yes, this is the relative velocity of A relative to B. Now, you're interested in the relative, in the temperature, and temperature is a measure. Well, we're taking an average. It doesn't depend on which side is positive, because, well, these are vectors. Vectors can have any direction. Now, what you need to understand, that's if you are sitting on a particle A, some particles are moving towards you, some particles are moving away from you. The ones that are moving away from you have a lower velocity because you're moving in the same direction. Some particles are moving towards you, so they have double the velocity. Some particles are moving up, some particles are moving down, and then you have to use Pythagoras to work out their relative velocity. But on average, the velocity is going to be bigger. Velocity of the relative velocity between particles is going to be bigger. So particles, if you're sitting on one particle, on average, the other particles have a larger speed than if you were stationary. And if you square both sides, now VA relative squared is going to be VA squared minus 2 VA VB plus VB squared. But this depends on the angle. It depends. VA VB depends on the angle between the vectors. Sometimes it is positive, sometimes it is negative. So you need to use the. Oh, I'll show you why right now. So if you were to sum up all the particles, this would sum up to 0 because the angle between the velocities is absolutely random, and therefore all the velocities will add up to, or all the products, all the scalar products of velocities of particles will be 0. And that means that on average, the sum of VA relative squared is the sum of VA squared plus the sum of VB squared. In other words, VA relative squared is double VA squared, because these have to be equal because we're talking about two random particles. And VA relative is square root of 2 VA. So that's the explanation. It's a very mathematical explanation, but you can think of it. So you are particle A and you're flying. And let's say we have 4 particles. One is moving towards you, one is moving away from you, one is moving up, and one is moving down. And let's assume that all the velocities are v. So if you are stationary, then the average velocity, the average speed is v. That's obvious because they're all moving with speed v. Now, if you are moving with velocity v, then what do you see? Like this particle is moving at 2v. This is moving v. This is moving v, and this is not moving at all, 0. So v squared. So this is v squared plus 2v squared. That is 4, 5, 6 v squared divided by 4. So divided by 4, so V average is 1.5 V squared, and that's clearly greater than V squared. So even for this simple example where you have just 4 molecules, you can show that the average square velocity is bigger. Oh no, sorry. Sorry, that was a minute of my madness. No. Forget what I did. You need to calculate the individual velocities, and that's not V. This is 2V, but this is, you need to use Pythagoras. So that's square root of 2V, because you need to find the velocity relative to u, and the relative velocity relative to u is square root of 2. And then you add the squares. V average squared is 2V plus 2V plus 4V. It's still the same. Squared. Yeah, I mean, still the same. 6 over 4 V squared, which is greater than V squared. We use the root mean square speed in thermodynamics because we are adding kinetic energies of the particles. The kinetic energies of the particles are proportional to the velocity squared. So we have to use velocity squared. So if you're stationary and the particle is moving v with the velocity v, that means relative to you, the speed is v. But if you're moving and the particle is moving up, that means the speed relative to you, that's v and that's v, is root 2v. Yes, it should be. It should be 8. That's 2. That is 2 root v, which is greater than v. And it's actually exactly what we expected. The average velocity relative is root 2 v average. That's what we got exactly. Sorry. I think the New Year's has thrown me off. Yeah, so if you're stationary, if you're moving and another particle is moving, then your velocity relative to that particle is has changed. Anyways, and that means that we just need to introduce another term here. So if you're not assuming that the particles are stationary, then lambda is kt over square root 2 p pi 4r squared. And then you can do the calculation. It says for a helium in a helium balloon. Okay, so that is just going to move this aside so it doesn't interfere. No, it doesn't want to. Anyways, estimation. So that's k, which is 1.38 times 10 to the minus 23 times the temperature. So take room temperature. So 293 square root 2 times pressure. So yes, take atmospheric pressure, 100 times 10 to the 3 times pi times 4 multiplied by 1 nanometer, so 10 to the minus 9 meters. Right, so if we calculate that, 1.38. 1.38 is 10 to the minus 23 multiplied by 293 divided by root 2 divided by 100,000 divided by pi divided by 4 divided by 1 to the power minus 9. So that's 2.3 times 10 to the minus 18 meters. Oh, it's squared. Minus 9. Yes, 1 nanometer squared. Thank you. 2.3 times 10 to the minus 9 meters. And yeah, that's very reasonable. So a helium molecule travels about the distance of about 2 helium molecules before colliding with another one. Very reasonable. Okay, good. So I hope this makes sense. Good. Now we're going to talk about the first law of thermodynamics. First law of thermodynamics is pretty much conservation of energy. If you do work, if you want to change the internal energy, if you want to increase, for example, if you take your hands and you rub them together, you increase their temperature. Okay, if you had an infrared camera, you would see that they are glowing red after rubbing. Now, if you put your hands on a heater, that also heats them. If you rub your hands against the heater, that will increase the temperature even more. Therefore, if we're talking about a gas, to increase the temperature of a gas, you can heat it or you can do work on the gas. You can increase the temperature of a gas by first heating and two by doing work. So the first law of thermodynamics can be written in the following way. There's many different ways, but I think the typical one is that the heat supplied to a gas, Q, is used to do work plus increase the internal energy of a gas. So it's a slight rephrasing of this. So if you supply heat to a gas, the gas does work and increases internal energy. So heat supplied is used to do work and increase internal energy. If we're talking about a gas and we're talking about a ideal gas, that then U is simply the sum of the kinetic energies of all the particles. Okay, but that's the first law of thermodynamics. Yeah, exactly. You can do the change of the internal energy of a gas. You can change the internal energy of a gas by supplying heat to the gas or doing work on the gas. Now, you might think that this is a contradiction. Delta U is Q plus work. This depends on how you read it. In this case, heat supplied is used to do work. So who is doing the work in this question? Well, the gas is doing the work. This is the work done by the gas. Doing work on the gas. So this is doing work on gas. So these are different W's. That's why, hence the confusion. If you write the work done on the gas, work done on gas is equal to minus the work done by the gas, then everything falls back into place. What you need to say is who's doing the work? The gas is doing the work, or are we doing the work on the gas? And you have two different ways of writing the same thing. Confusing, but get used to it. I think the best way is just to adopt one way of writing it. Like the first one is the one that I was explaining. You can increase the energy of a gas by heating it or by doing work on it. Or another way of saying is that the heat that you supply to a gas is used. This is more like machine thinking. Like you're supplying heat to a engine, and you want to know how much work is done by the engine. So that's another way of looking at it. But anyways, that's the first law of thermodynamics for you. Now, depends on what the question asks. Typically, if you have if you don't need to do any integration, you don't need the differential form. Okay. Types of processes and cycles. Well, there's three processes that are quite interesting. Like if you take PV diagram, then a process at constant pressure is called isobaric. That means the volume is changing, but the pressure is not changing. It's an isobaric process. If your volume is not changing, but the pressure is changing, that's called an isochoric process. If the temperature is not changing, this is called an isothermic process. So isobaric, isothermic, isochoric. Isothermic, so isobaric is the pressure is constant. Isothermic temperature is constant. And isochoric is volume is constant. There's another process that you need to know. It's called an adiabatic process. It's steeper than isothermic. Adiabatic. Adiabatic process means that the heat supplied to the gas is zero. Okay. If you can draw these processes in on a different scales, different diagrams. So PT, for example. So this would be isobaric. Isobaric. This would be isothermic. Thermic. Now, if volume is constant and isochloric process would be like this. Isochoric. So in an isochoric process, P is proportional to T. Okay. And finally, VT. VT. I don't know if adiabatic is ever drawn on a PT diagram. I've never seen an adiabatic process drawn on a PT diagram. I'll think about how it looks like, maybe draw it later. VT, so on a VT diagram, so this would be isochoric. This would be an isothermic. And this would be an isobaric. Isothermic. Okay. In order to explain what adiabatic process is, let's get back to the equation. So the heat supplied to a gas is used to increase the, what am I saying? Is to used to do work plus increase the internal energy of a gas. Apologies. So in an isothermic process, the temperature is not changing, is constant. And that means that the change in internal energy is zero. And that means that the heat supplied to the gas is equal to the work done by the gas. So you supply heat to a gas and it does the same amount of work. In an isochoric process, the volume is constant. And if the volume is constant, that means that no work is done by the gas. To understand this, let's assume we have a piston. And the piston has an area A. Area is cross-sectional area of the piston. The pressure of the gas is P. So the work done is force multiplied by the distance moved. So the piston, assume the piston moves by a distance d. Okay. But force is pressure times area. Pressure multiplied by area multiplied by the distance moved. But if you were to find the volume of a gas, so the initial volume, so if I ask you the question, by how much did the volume change? What is the change in volume of the gas? Well, if the piston moved by a distance d and the cross-sectional area is A, then AD is the change in volume of a gas. And you can substitute that back in. So it's P delta V. So the work done by the gas is pressure times the change in volume. Pressure times the change in volume. And because there's no change in volume, in an isochoric process, the work done by the gas is 0. And from this equation, we can say that Q is equal to delta U. So all the heat supplied to the gas goes into increasing the temperature of the gas. In an isobaric process, pressure is constant. Well, there's nothing special here. Nothing is 0. So basically, you still have the same equation. Q equals W plus delta U. Now, for the adiabatic process, it is a process that is very quick, usually very quick. So in this case, Q is 0. There's no heat supplied to the surroundings and no heat absorbed from the surroundings. And you can say that work done is minus delta U. In other words, the gas is doing work, but it is losing energy. So the gas is using its internal energy to do work. What would be an example of that? Well, for example, the air is heated by the sun, and the ground is heated by the sun. It heats up the air just above that ground. The air rises, the warm air rises, but because the pressure drops, the gas expands. And as the gas expands, it cools down because it's doing work. To expand, it has to do work, and because it's doing work, it's cooling down. That's one way of looking at it. Is du the same as potential energy here as the kinetic energy is accounted by the work done? No, du is the sum of kinetic energies. Literally, du for an ideal gas, du is yes. Okay. So I think I'll do these 2 questions and then we'll finish. An ideal gas undergoes the thermodynamic changes represented in the PV diagram below. Which of the following is the net work done by the gas in a cycle? So we need to first figure out so we know the work is pressure times delta V. On a PV diagram, if you have a process, you'd also the area PV, so area is the work. So in the process PQ, the gas is expanding. So PQ is expansion of gas. So the work done by the gas, the work done in the section PQ is pressure times the change in volume. So pressure is 3 times 10 to the 5 multiplied by 1. Joules. That's the work done in PQ. The work done in the section QR is P times delta V, but delta V is 0. Therefore, it is 0 joules. So the gas is not doing work. This is an isochoric process. In an isochoric process, the volume does not change. Therefore, the work is 0. Finally, in the process RP is the area under the graph. And we need to take the average pressure multiplied by change in volume. Therefore, that is 2 times 10 to the 5 times the change in volume is 1 cubic meter. So that's 2 times 10 to the 5 joules. But the gas is shrinking. That means work is done on the gas. That's on the gas. So the work done by the gas is negative. So the total work is 3 times 10 to the 5 minus 2 times 10 to the 5. And that is 1 times 10 to the 5 joules. And the answer is C. The question is not very well formulated, because if I was doing the question, I would probably say the answer is B. Because on the section RP, the gas is doing negative work. Or you could say someone else is doing the work on the gas. So I would argue that gas is only doing work on the PQ section. But the authors of this question, they went another way. So just something to look out for. You need to be very clear what is being asked. So PV diagram shows the expansion of a fixed mass of an ideal gas from state A to state B. So the gas is expanding. How do we know it's expanding? Well, we know that the pressure volume is increasing. The temperature of the gas, so it's 400 Kelvin here. Calculate the temperature in state B. Well, we need the equation of state. So PV equals NKT. So the TA is PAVA over NK. And we know that this is 400 Kelvin. Here. PV is PB VB over NK, and N is the number of molecules, K is the Boltzmann constant. Now, rather than trying to work this out, we can Work out what PAVA is. Well, PA is 8 and V is 4. So PAVA is 3200. Now, if you calculate PBVB, this would be 4. So in other words, PAVA is equal to PBVB. And I can substitute that in, and I will see that the answer is 400 Kelvin as well. So the temperature of B is 400 Kelvin. In other words, points A and points is the process AB, does that mean that the process AB is a isothermic process? What do you think? Can you explain why? A very simple explanation would do. Isothermic process is not. Abiole, exactly. The temperature has changed during process and then changed back. Isothermic process is a curve. On the PV diagram, the isothermic process is a curve. And this is clearly not a curve. So an isothermic process would go like this. So the temperature increased and then decreased back to 400. So the temperature here would be more than 400, and then it comes back. So it's 400 Kelvin. Calculate the work done by the gas expanding from state 8 to state B. Well, the work is pressure times delta V. We take the average pressure. The average pressure is 6 times 10 to the 5. Multiplied by change in volume, that's 4 times 10 to the minus 3. That is 2400 joules. Determine the amount of thermal energy transferred during the expansion from state A to state B. So to do this, we need Q is equal to the work done plus delta U. But delta U is 0 because the temperature has not changed. Therefore, Q is W, which is 2400 joules. The energy transferred to the gas is 2400 joules. The gas is either isothermically compressed from state B to state A. Draw the variation of pressure with volume for this iso. Okay, I've already done that, so that would be this arrow from B to A. State and explain whether the magnitude of the thermal energy transferred in this case would be less than, equal to, or greater than the thermal energy transferred in B. Well, Q is work plus delta U. Delta U is still 0 because the temperature hasn't changed, but Q is work. But work in isothermic process is the area under this curve, and that's less than the area of the trapezium. isothermic, which is less than the work done in the process AB. Therefore, less work is done. Therefore, less heat is transferred. It's quite interesting. You go from the same state to another state, but you're doing different amounts of heat supplied. Okay, I think I'll finish here. Sorry for being a bit hectic at places. Please do watch other webinars. And I'll see you, I think it's next week. Let me check. 9th. Yes, that's exactly a week from now for the Gauss function. All right. Enjoy your week and welcome back. See you.